By now you know quite a bit about a single average, but sometimes we find ourselves comparing averages in questions such as, how has the cost of living increased on average? And when comparing averages, there is one point to note, and that point makes the comparisons sensible. And I'd like to illustrate it by an example. So here are some data on the average height of US men in different age groups. Heights are measured in inches. These are US units. By now, you know how to read such a table. And so I won't go into great detail other than to say you have the men in their 20s, 30s, 40s, 50s, 60s and up. And you have here the average height of each group. And the question I'd like to ask you is this. Is this table telling us that as men get older, on average they get a little bit taller and then get shorter? Certainly 67.2 is 2 whole inches less than 69.3, so someone's shorter. But is that really what you see as men get older? There's something a little bit disquieting about this. And in fact, the data were not gathered by watching a group of men as they aged, because you can see that the data were gathered over a period of 3 years, certainly not long enough for somebody to grow from age 20 to age 75. These data are not longitudinal. Longitudinal is when you follow your group of subjects over a period of time. Rather, these data are cross-sectional. The table is a snapshot of the population at a particular time over this little period of time, which is a relatively short period compared to the decades that are passing in the table. And so what is clear is that the men who were in their 20s in the study were a different group of men from those who were in their 60s and 70s. So what have you learned from this table? What you have learned simply is that the older men were shorter, on average. You have learned nothing about a man as he ages. Now, why are the older men shorter? That you can't tell from the table, but perhaps you can think historically these men were born many decades before the men in their 20s. Nutrition has improved. When these men were young, there had just been a war. Possibly that's the issue. Californians will tell you that it's the growth hormones in the milk that is making our young people get taller. I'm not so sure about that. But I am sure that these men were different from the younger ones, and they are just shorter than the younger ones. That's all I learn from this table. And so when comparing the averages of different groups, it's a great idea to start by looking at the groups first, not at the numbers, not at the averages themselves. How are the groups related to each other? If you can answer that question, then when you compare the numerical averages, you may have more insight into why the averages are behaving as they are. You recall when you started looking at graphs, how your eye was drawn to the graph itself, and maybe to the vertical axis, but how you really had to force yourself to look at that horizontal axis. This is sort of the same thing. Don't start with the numbers, start with the groups on whom those numbers are based. And so here's another place where you should look at the groups first. This is a situation where you want to combine two averages. So supposing you know the average educational level of men and the average educational level of women, then can you find the average educational level of all the adults? I'll do a simpler example where I have a class that has been split into two sections, and the class takes an exam, and section 1 averages 60 and section 2 averages 70. And the question is, what is the class average then? And there's a natural first answer which says, let's take the average of 60 and 70. And that average is 65, which is a comfortable answer. It's halfway in between 60 and 70 and just seems all fine, except when you start considering extreme cases. So for example, supposing this section 2, had 100 people in it, whereas section 1 had one poor lonely person. Yes, I know that's an extreme, but I said it was going to be an extreme, bear with me. Then when you combine the groups, you have 101 people, and it just doesn't seem plausible that this one person's score, low as it is, should pull the entire group's average down by 5 points. Something seems wrong. And in fact, this question can't be answered with the information given. So no, it is not okay to just take the average of the averages. There is something else going on. It has to do with the relative sizes of the sections. What you can say is that the class average has to be between 60 and 70. It cannot be anywhere else. But exactly where will depend on how big the sections are relative to each other. So if I told you the section sizes, then could you do it? Oh, I think so. What is it that we're trying to find? We're trying to find the class average. And what is the class average by definition? It is the total score of the class, add up all the scores, and divide by the class size. So which of these two bits do we know? Well, we certainly know the class size. 20 students in one section, 30 students in another, 50 in all. So what we have to find is the total score in the class. That is not so apparent from the table. However, we should be able to think about the total score in section 1. So if you recall, when we talked about the average as a smoother, we said the average being 60 means that each of these 20 students gets a fortune, if you like, of 60 points. And if that's the case, then the total must be 60 times 20. And if that's the total in section 1, then you can find similarly the total in section 2, and you have the total score of your class, which is 20 times 60 for the total of the first section, 30 times 70 for the total of the second. Add all of that up and you get 3,300. So that's the total score of the class, divide by 50, and bang, your average is 66. You're done. And so this is how you combine two averages, taking into account the number of entries that went into each one. What I would like to do now is examine the arithmetic a little bit more closely to notice something that will help us later and also explain why we had 65 as our first guess at an answer. So we've had the sense for some time that the class average will depend on the relative sizes of the sections, so it seems like a good idea to look at the proportion of the class that is in each section. So in section 1 you have 2/5 of the class, 20 out of 50, and in section 2 you have 3/5. And so if you look at the calculation for the class average, then it's the total in section 1 plus the total in section 2 divided by 50. This is what we did before. And now I'm going to do a little arithmetic. I am going to distribute this division across the sum on top. And I will end up with the 60 getting multiplied by 20 over 50 plus the 70 getting multiplied by 30 over 50. So these two calculations give exactly the same answer. The one on the left says, do the addition first, then divide the whole thing by 50. The one on the right says, do the division first, and then add the two pieces. Works out the same either way. And once we've written it this way, well, you see a couple of zeros cancelling, and what you have is the class average is 2/5, which is the proportion in section 1 times the average in section 1 plus the proportion in section 2 times the average in section 2. And if you work that out, you get 66, which is what we got on the last slide. And so we say that the class average is the weighted average of the section averages. So it is a kind of average of 60 and 70. It's just that attached to each of 60 and 70 is the weight, which is the proportion of students who were in that section. Now, had the sections been of the same size, then the proportions would have been half and half. And then you'd have had half of 60 plus half of 70, and you'd have had 65. So our first guess answer, just average these guys, is correct in the situation where the section sizes are the same. But otherwise, we have to take the proportions into account, thus.